Hello students, welcome back. So first let us start Brahmanath. So last class we have studied what is conductance, what is resistance, and what are the factors affecting conductance, what is Kohler's law, how to determine the conductance of equivalent conductance, molar conductance, and specific conductance of electrolytes, weak electrolytes and strong electrolytes. Okay, so today now here we are going to study about another part of electrochemistry, that is electrochemical cell. Electrochemical cell. So what is electrochemical cell? So electrochemical cell is a device which convert the chemical energy to electrical energy. So it is a device which convert chemical energy to electrical energy. That means electricity is produced as a result of redox reaction and decrease in free energy change. Actually, this is electricity device where electricity is produced as a result of indirect redox reaction. And this reaction is generally spontaneous, hence the free energy change is negative. Okay, so it is a device where electricity is produced as a result of chemical reaction or as a result of redox reaction. Okay, so generally so what is the construction of this device, how this device works, let us discuss one by one. So first, the construction. So generally redox reaction takes place in here I have to do that redox reaction takes place in indirect way. So if the direct reaction in generally electrolytic cell, direct redox reaction takes place. But here in electrochemical cell, indirect redox reaction takes place. And as indirect redox reaction takes place, and generally this takes place in two compartments. Okay, so electrochemical cell, it consists of two compartments. It consists of two compartments that are called voltmeters and two different electrolytes are taken here. Two different electrodes are taken here. Okay, two different electrodes are taken here, and these two are connected through internally through salt. These two electrolytes are connected through a salt bridge. And these two electrodes are connected through a galvanometer, conductor wire and a galvanometer. Okay, so for example, so this consists of two compartments and two different electrolytes, two different electrodes, a salt bridge and conducting wire and a galvanometer. Okay, so this is the construction of, in general construction of an electrochemical cell. Let us consider the example of Daniel cell. This electrochemical cell are also called voltaic cell. These are also called galvanic cell. These are also called galvanic cell, voltaic cell, the different name of electrochemical cell. And one example is Daniel cell. You can say Daniel cell is one type of galvanic cell, or Daniel cell is one type of electrochemical cell. And in Daniel cell, generally what is taken, this is also called zinc copper sulfate system. Okay, this is also called zinc copper sulfate system. Here a zinc electrode is used. A zinc electrode dipped in zinc sulfate solution. So this is the zinc sulfate. The electrolyte is here zinc sulfate solution, and a copper electrode dipped in. This is the copper electrode and dipped in copper sulfate solution. So this is dipped in copper sulfate solution, and this is zinc rod dipped in zinc sulfate solution, copper rod dipped in copper sulfate solution. Then these two are connected through the conducting wire and a galvanometer or an ammeter, and these two electrolytic cells are again connected with a salt bridge. So this is a salt bridge. So what is the salt bridge? The salt bridge is an inverted U-shaped tube which contains inert electrolytes. So salt bridge, generally it contains an inverted U-shaped tube. Inverted U-shaped tube contain inert electrolyte like potassium nitrate, potassium chloride, potassium sulfate, etc., which do not react with this electrolyte. Okay, and generally these electrolytes, concentrated solutions of these electrolytes are taken in the salt bridge in agar-agar jelly, in agar-agar, or in gelatin. So these electrolytes these are the concentrated solution of these electrolytes contains in agar-agar, in gelatin, packed within gel form, and here the cotton plug or cotton or glass wool is by which it can be closed. The two openings of this tube are closed with cotton wool or with glass wool. Okay, so this is helpful for the fusion of, for the transfer of, this is generally helpful for the transfer of different ions. Okay. So what is the functions of salt bridge here? So the salt bridge, it completes the circuit. You know, in externally these are connected through externally these two compartments or these two beakers two voltage cells are connected through conducting wire, and internally these two are connected through a salt bridge. So in this it completes the circuit. The salt bridge, it completes the circuit, and it maintains the electrical neutrality of the cell, and it prevents the liquid-liquid junction potential. Liquid junction potential. So these are the functions of salt bridge. So a salt bridge completes the circuit. So it maintains the electrical neutrality of the cell and prevents liquid-liquid junction potential. So potential that develop due to the combination of two different electrolytes. Okay. So zinc rod dipped in zinc sulfate and copper rod dipped in copper sulfate. A salt bridge is there. It may contain potassium nitrate, potassium chloride, potassium sulfate in agar-agar or in gelatin, agar-agar or gelatin, and a galvanometer is connected here through this conducting wire. Okay. Next, what is the working process? How this works? Okay, so next come to working process. So zinc has the tendency to lose electron than that of copper. Okay, so first zinc, here some amount of zinc from this electrode is come to from this solution. So zinc first converted Zn2 plus 2 electron. Zinc first converted to Zn2 plus and 2 electron. So here Zn2 plus are accumulated and these 2 electrons move through. So it becomes now electron rich. As it becomes electron rich, it now becomes the source of electron. So this becomes the source. This half cell, so this half becomes the source of electron. It becomes the source of electron and zinc has to give zinc plus electron and zinc this Zn2 plus ion comes to the solution. Zn2 plus ion comes to the solution and these 2 electrons move through this conducting wire and goes to this copper and accepted by this copper sulfate ion. Here copper sulfate is there. Now this copper sulfate, copper is in Cu2 plus form. Now this Cu2 plus receives this Cu2 plus receives this 2 electron and is converted to copper, metallic copper, which is deposited around this electrode. So now Cu2 plus 2 electron gives Cu. Okay. So here now this half is known as the sink of electrons, and this is the source of electrons. Okay, so what happens in this zinc rod? So Zn give rise to Zn2 plus 2 electron. What happens here? Loss of electron takes place, and Cu2 plus gives you Cu2 2 electron plus Cu. So what happens here? Gain of electron takes place. So where loss of electron takes place, that is known as your oxidation, and where gain of electron takes place, that is known as your reduction. So what happens here? Here oxidation takes place and here reduction takes place. Now it becomes the source of electron, more electronegative. So now this becomes, this half is known as your anode, and this half where electrons are received, that is known as your cathode. Okay, so in general this cell consists of 2 half cells. Now this total complex cell, this electrochemical cell, consists of 2 half cells. The one half cell where oxidation takes place is known as oxidation half cell. Where loss of electron takes place, and now it becomes the anode. So in anode, oxidation. Okay, remember anox and red cat, oxidation, anode, and reduction at cathode. And so this half cell where oxidation takes place is known as oxidation half cell, and here the cell where reduction takes place. The other half part where reduction takes place, that is known as reduction half cell. And this is the electron, it is known as your cathode. So in anode, loss of electron, in cathode, gain of electron. So anode is oxidation half cell and this cathode is the reduction half cell. Okay. So now the electron moves through the external circuit from anode to cathode. This copper electrode is known as cathode, this zinc electrode is known as anode. Electron moves through the external circuit from anode to cathode, and current flows from cathode to anode. So current flow of current in external circuit from cathode to anode. So conventional current conventional current that flow from cathode to anode. Okay, so here from anode to cathode, electron transfer takes place, and from cathode to anode, current flow takes place, which can be known by the deflection of a galvanometer. As the galvanometer deflected, from the deflection of galvanometer, the flow of current can be known. Okay. So this is the working process. So what is the general reaction? So zinc give rise to Zn2 plus 2 electron, and copper give rise to copper ion. Here the copper ion is there. Copper plus 2 electron give rise to copper. So what happens after some time? What is the first? Let us discuss what is the general cell reaction. The general cell reaction is Zn plus Cu2 plus give rise to Zn2 plus Cu. This is the overall cell reaction. This is overall cell reaction. This is oxidation half cell reaction. This is reduction half cell reaction. Oxidation half cell reaction, reduction half cell reaction, overall reaction. Okay, so what happens during this process? So during this process, zinc is first converted to Zn2 plus ion, and this is accumulated here, and the electrons are moved here. So as the zinc concentration of zinc is present in the solution becomes more, and zinc loses its mass and converted to Zn2 plus. After some time, the weight of this zinc rod decreases. Now this zinc rod loses its mass, zinc rod loses its mass or its weight decreases, and the concentration of the solution increases because it contains more amount of Zn2 plus ion. Similarly, this electron move towards it. Here the copper Cu2 plus ions are there in copper sulfate, and the Cu2 plus ions receives electron, and metallic copper deposited on this copper electrode. So as in copper electrode, the metallic copper deposited, after some time there is gain of weight. So some amount of copper deposited here. In this way, in cathode or in copper electrode, there is gain of weight or gain of mass. So here copper electrode or the cathode gains its mass, whereas the anode loses its mass. And what happens to the solution? And the Cu2 plus ions are converted to here, they move to here. This copper is deposited. After some time, the mass of the Cu2 plus concentration here decreases. Here the Zn2 plus concentration increases, and here the Cu2 plus concentration or copper 2 plus concentration decreases. Okay, so the concentration of this electrolyte increases, concentration of this electrolyte decreases, weight of this electrode decreases, weight of this electrode increases. So this is the general cell reaction. Okay, so what happens? So after some time, when the electrons are flowed, more amount of Zn2 plus ions are accumulated here, and here as Cu2 plus is converted to Cu, more amount of sulfate ions are accumulated here. So as more amount of Zn2 plus ions are accumulated here, now they don't allow the electrons to move again. They don't allow the electrons to move in the outer circuit. Similarly, as more amount of sulfates are present in cathode, if the more amount of sulfate is present in this reduction half cell or in cathodic cell, then it do not receive the electron, because you know sulfate is negative charge, and this negative charge is present more amount of here. In this way, it do not receive the electron. And similarly, as more amount of Zn2 plus ions are accumulated here, which do not allow the flow of electron. In this way, now there is the need of salt bridge. So what is the function of salt bridge? It contains salt. Suppose it contains the electrolyte like potassium sulfate, or it contains the electrolyte potassium chloride. Then Zn2 plus ions are there. Then it diffuses the sulfate ion from here to here. So it diffuses the 2K plus SO4 2 minus. The sulfate ion diffuses to here. In this way, it maintains So the electrical neutrality maintained here. Similarly, now it contains more amount of sulfate ion and it contains more amount of sulfate ion. Then the salt bridge diffuses this K plus ions towards it. As it diffuses the K plus ion towards it, in this way it also maintains the electrical neutrality. Okay, and the flow of ions takes place. So in this way, salt bridge helps for the flow of ions and also it maintains the electrical neutrality of the cell. Okay, so this is about electrochemical cell and how it works and how the electron flows and how the current flows and where oxidation takes place, where reduction takes place, and what is the general cell reaction of the ideal cell. So in oxidation half cell, Zn 2 plus 2 electron. In reduction half cell, Cu2 plus 2 electron. So in this way, so this is the reaction at anode, this is the reaction at cathode, and this is the overall reaction of electrochemical cell. Next, so always to represent this cell in diagrammatically, it takes more time as well as it takes more space. In this way, this cell can be represented in the symbolical way. Okay, so how to represent an electrochemical cell in symbolical way? Presentation of electrochemical cell. Suppose let us consider the example of same Daniel cell or zinc copper sulfate system. Zinc copper sulfate system. In zinc copper sulfate system, so if any one half cell where oxidation takes place, this is written in atomic form, and any case where reduction takes place, generally it is written in ionic form. So zinc copper sulfate system, from that we can know in zinc oxidation takes place and in copper reduction takes place. So now this is represented as anode and this is represented as cathode. So how to represent the electrochemical cell? For presentation of electrochemical cell, the two half cells are written. In the left hand side, the oxidation half cell, in the right hand side, the reduction half cell is written. Okay, so while you represent the oxidation half cell, first you have to write the element name or the electrode name followed by its ionic form, followed by its ions and the aqueous solution or what is the concentration of this, and these metal electrode and its ions, these are separated by a vertical column. Similarly, in the right hand side, the reduction half cell or cathodic cell is written, and here also the ions in the metals are separated by a single vertical line. Okay, so first in cathodic cell, first ion is written, then its metal or elemental form is written, and in between this cathodic symbol, it's an anode and cathode. In this between two half cells, generally two vertical lines are written, represented, which represents the salt bridge. For example, for zinc and copper sulfate system, this is written as Zn. This is in metallic form, so I can write solid. Then Zn 2 plus, that is in aqueous form, or if the concentration given, then that is written. Then it represents the salt bridge. Then Cu2 plus, this is in aqueous form. Okay, then your metallic. Okay, so this represents your what? Cathode, or that is your reduction half cell, and this represents anode, that is the general presentation of an electrochemical cell. Instead of aqueous, here the concentration of solutions, the electrolytic solutions are generally written. Okay. So let us consider another electrochemical cell, example of another electrochemical cell, that is copper and silver nitrate system, and we have to write what is the cell reaction. Represents this electrochemical cell and write down the oxidation half reaction, reduction half reaction, and the overall reaction. Suppose given copper silver nitrate. From this we can know this copper, from this presentation, from this name we can know in copper oxidation takes place, in silver reduction takes place, in silver ion reduction takes place, in copper oxidation takes place. So this is your oxidation half cell and this represents your reduction half cell. So how to write, how to represent this cell? Cu solid, then Cu2 plus aqua or Cu1 concentration given. Then some salt bridge, and what is the content in salt bridge that is written in between these two vertical bars. Suppose it contains potassium chloride, so I can write here potassium chloride. Potassium sulfate, I can write here potassium sulfate. Potassium nitrate, I can write here potassium nitrate. This, what is the electrolyte present in salt bridge that is written in between this vertical line or remain as it blank. So copper solid Cu2 plus and silver has valency 1 Ag plus. It is also in aqueous form and this is Ag solid. This is the presentation of cell. This is your oxidation half cell. This is your reduction half cell. And what is the cell reaction? So oxidation half cell reaction at NO. So what is that? Cu2 plus, Cu. So here copper loses electron, oxidation, Cu give rise to Cu2 plus 2 electron. That is what? It is at anode. Okay. What is the reduction half cell? Reduction half cell reaction. Reduction half cell reaction. What is that? That is takes place where? Okay, at cathode. So that is what is Ag, silver present at Ag plus electron give rise to Ag. So this is the reduction half cell. But the total electrons should be balanced. In this way it should be multiplied by 2. This is the reduction half cell reaction. And what is the overall reaction? Overall cell reaction, that is Cu plus 2 Ag plus, Cu solid plus 2 Ag plus, or you can write Cu plus 2 Ag plus give rise to Cu2 plus 2 Ag. So this is the 2 silver. This is the overall cell reaction. Similarly, suppose given any gaseous electrode, suppose hydrogen electrode is given. Here given zinc HCl or zinc hydrogen electrode. So you know hydrogen is a gas that cannot be directly used as an electrode. So for hydrogen, if there is hydrogen, some gaseous electrodes are there. For that we have to use some metal electrode. We have to use some metal electrode. And how to represent this zinc HCl cell? So for this zinc HCl cell, generally Zn2 plus, then salt bridge, then H plus, this is in aqueous form, This is H plus, this is also in aqueous form. Then H2 and a metal electrode as used platinum. Here you have to write the platinum electrode. Or if graphite present, then you can write carbon like this. So what is the element, other element used for gaseous electrode? You have to write the gaseous gas which is present in molecular form, and along with it you have to write this what inert electrode you have used here. So for hydrogen electrode it can be represented like this. Suppose suppose I write another, that is your H2SO4, and suppose H2SO4 in one case and another case, that is your copper sulfate system. Suppose one contains electrolyte H2SO4 and copper and hydrogen electrode, or I can write H2CuSO4 system. So in this case H2CuSO4 system, how to write this? For that you have to write this platinum electrode, then hydrogen in gaseous form, okay, then H plus ion in aqueous form, or then you have to write the salt bridge, then Cu2 plus in aqueous form, then Cu solid. So in this way the hydrogen copper sulfate electrode can be represented and zinc HCl can be represented. And what is the cell reaction? Suppose I am writing the cell reaction for this. So first H2 give rise to 2H plus 2 electron, loss of electron, and Cu2 plus 2 electrons give rise to Cu, and overall reaction H2 plus Cu2 plus give rise to 2H plus Cu. So this is the general presentation of an electrochemical cell and how to write the cell reactions. Okay. Next come to another factor of this electrochemical cell, that is another term of this electrochemical cell, that is electrode potential. So what we have seen in this electrochemical cell. So I have taken two examples. One is your zinc copper sulfate system, another your copper and silver nitrate system. In zinc copper sulfate system, copper rod acts as your cathode, whereas in copper and silver nitrate system, copper rod acts as your cathode. So how, whether the same element or the same electrode can act as cathode or anode, whether it has the tendency, so that can be known by the term that is known as your electrode potential. So actually what is electrode potential? So this is the tendency of an element or an electrode to lose or gain electron is known as electrode potential. So the tendency of an element or an electrode to lose or the gain electron is known as electrode potential. So it is the tendency. The tendency of an element, or electrode to lose or gain electron is known as electrode potential, and the tendency to lose electron is known as oxidation potential. And the tendency to gain electron is known as reduction potential. The tendency of an electrode tendency of what? An electrode to lose electron is known as oxidation potential, but the tendency of an electron to gain electron is known as reduction potential. Okay, so this reduction potential of the oxidation, so what is the value of an electrode or what is the reduction potential of an electrode? From that we can calculate what is its oxidation potential. So the reduction potential of an electrode, reduction potential of an electrode is just negative of its oxidation potential. The reduction potential of an electrode is just the negative of oxidation potential. This is the negative of its oxidation potential. Or we can say the oxidation potential of an electrode is just the negative of its reduction potential. Okay? So the oxidation potential just the negative of reduction. So suppose that for zinc electrode, the oxidation potential given. Then how to determine its reduction potential? Just by changing this sign, the negative. Okay. Similarly, what is the numerical value of oxidation potential, reduction potential is same, but just by changing the conventional sign, the oxidation potential and reduction potential of an electrode changes. Okay. So this electrode potential depends on different factors, that is your temperature, concentration, this nature of electrolyte, etc. So it depends on the electrode potential, also depends on the concentration of the solution and temperature. Generally, with increase in concentration, the reduction potential increases and the oxidation potential decreases. Okay, so oxidation potential. Generally, the reduction potential is directly proportional to the concentration of the solution, and this oxidation potential is inversely proportional to the concentration of solution. Okay. So, this is about some idea about reduction potential and oxidation potential. So, the reduction potential or the this oxidation potential or this reduction potential, if it is measured at standard condition, if it is measured at standard condition, that is at 298 Kelvin and 1 atmospheric pressure, if the electrode potential measured at standard condition, that is just 298 Kelvin, 1 atmospheric pressure and 1 molar solution, then the electrode potential is known as standard electrode potential. Then the electrode potential is known as standard electrode potential and represented as E naught and represented as E naught. This naught stands. Next, so standard condition. So electrode potential measured at standard condition, that is at 298 Kelvin, 1 atmospheric pressure and 1 molar solution. 1 molar solution is known as standard electrode potential and is represented as E naught. Okay, is represented as E naught. So this is also called standard electrode potential. Similarly, suppose you take the zinc sulfate. For zinc, standard electrode potential of E naught of zinc electrode, for you have to take 1 molar solution of Zn sulfate. If 1 molar solution of Zn sulfate taken at 298 Kelvin and at 1 atmospheric pressure, generally this 1 atmospheric pressure is used for gaseous electrode, for gaseous electrode, and for normal other electrode. Generally we are using 1 molar solution and at 298 Kelvin. The electrode potential measured is known as standard electrode potential, and the standard electrode potential may be standard oxidation potential or may be standard reduction potential. Suppose the cell reaction, electrode reaction is Zn2 plus 2 electron give rise to Zn. So here gain of electron, this is known as standard reduction potential, and we can write E naught Zn2 plus by Zn. So Zn2 plus reduction takes place. So this is the presentation of standard reduction potential. Standard reduction potential. This is the presentation of standard reduction potential. Similarly, suppose reaction takes place, Zn give rise to Zn2 plus 2 electron at standard condition. For that, what we can write for this? This is for Zn2 plus 2 electron give rise to Zn. This is, and if the cell reaction is Zn give rise to Zn2 plus 2 electron, here what? Loss of electron takes place. For that we can write Zn and Zn2 plus. Look here, this is very important. If metal then followed by metal ion, this represents your oxidation potential. This represents your oxidation potential. If metal ion followed by metal, then that is your reduction potential. So E naught, that represents your standard oxidation potential. It is very important to identify whether oxidation potential retained or reduction potential retained. If metal ion followed by metal, that is your reduction potential. Metal followed by metal ion, then that is your oxidation potential. Okay. Next come to cell potential. So this is about electrode potential. Now next come to cell potential. So to find out this, in a cell, electrochemical cell, it consists of two types of electrodes. One is anode, another is cathode, or two half cells. One is oxidation half cell, another reduction half cell. So how to find out the cell potential? Suppose we want to find out the standard cell potential. The standard cell potential. So this is the potential difference between two half cells in terms of either oxidation potential or in terms of reduction potential. This is the potential difference between two half cells in terms of either oxidation potential or in terms of reduction potential. But for conventional method, generally reduction potential is used. Okay, so standard cell potential represented as E naught cell. This is equal to E naught cathode minus E naught anode in terms of reduction potential. So if you take the reduction potential term, then cathode minus anode. This represents the E cell. Okay. So reduction potential of reduction half cell minus reduction potential of oxidation half cell. We can write reduction potential of reduction half cell minus oxidation reduction potential of reduction potential of oxidation half cell. So reduction potential of reduction half cell minus reduction potential of oxidation half cell. So this is your standard cell potential. Suppose we are to determine in terms of anode oxidation potential, then in terms of oxidation potential, how we can determine? It is of E naught anode minus E naught cathode. That is in terms of oxidation potential. If you consider the oxidation potential of both, then anode minus cathode. If you consider the reduction potential of both, then cathode minus anode, that is E naught cell. And if you consider the oxidation potential of anode and reduction potential of cathode, then also this E naught cell we can determine, that is E naught cathode minus E naught anode. Here, E naught cathode plus E naught anode in terms of reduction potential and in terms of oxidation potential. So reduction potential of cathode plus oxidation potential of anode, that gives you the cell potential. Similarly, E naught cell, E naught cathode minus E naught cathode. So in this way you can determine the cell potential. So this cell potential, to find out the cell potential, we have to find out what is the standard electrode potential of an electrode. Then how we can determine the standard electrode potential of an electrode? Suppose we want to find out the standard electrode potential of zinc. Suppose we want to find out the standard electrode potential of copper. Suppose we want to find out the standard electrode potential of silver. Then how we can determine? If any electrode is dipped in its own ion, electrolyte of its own ion, then after some time there is no loss or gain of electron. After the achievement of equilibrium, actually there is no loss or gain of electron. If the zinc rod dipped in zinc sulfate solution, or a copper rod dipped in copper sulfate solution, or a silver rod dipped in silver nitrate solution. So after the achievement of equilibrium, there is no loss or gain of electron. Then how we can determine this standard electrode potential at that time? So for that we have to use a reference electrode. For that we have to use a reference electrode. The reference electrode, with the help of reference electrode, we can determine what is the electrode potential. Okay. So to measure the standard electrode potential of any electrode, generally we have to use a standard electrode, a reference electrode. So here there are different reference electrode like calomel electrode, standard hydrogen electrode, etc. So here the simple one is the standard hydrogen electrode. Okay, standard hydrogen electrode, or we can say this is the normal hydrogen electrode. Normal hydrogen electrode. Okay, so in this normal hydrogen electrode there is a glass tube, and this glass tube again fitted with another glass tube which is fitted with platinum black. There is a glass tube fitted with platinum wire, connected platinum wire, and a platinum electrode coated with platinum black. This is platinum electrode coated with platinum black, and this is the platinum wire. Okay, and the platinum electrode connected with platinum black, platinum powder, and this is another glass tube which is with there is a passage for the there is inlet for the passage of hydrogen gas, for any gas. So here 1 m hydrochloric acid is taken as the electrolyte. 1 molar hydrochloric acid is taken as the electrolyte, and temperature is maintained at 298 Kelvin. Temperature maintained at 298 Kelvin. solution is 1 molar. This is taken as electrolyte, and hydrogen gas at a pressure of 1 atmosphere is bubbled through it. And this, when hydrogen gas is bubbled, so this arrangement, this setup is known as your standard hydrogen electrode. So in standard hydrogen electrode, the hydrogen gas is passed through it at standard condition, that is 1 molar hydrochloric acid, 298 Kelvin, and at 1 atmospheric pressure. So this is known as your standard hydrogen electrode or hydrogen electrode. And this electrode is then coupled with, this is connected with other half cells. So now it may become oxidation half cell, or this electrode may become reduction half cell. So now this is known as your reference electrode, and arbitrarily the electrode potential of this hydrogen electrode is taken as 0.00 volt. Arbitrarily, the standard electrode potential of this hydrogen electrode EH plus H is taken as arbitrarily. The electrode potential of this hydrogen electrode is taken as 0.00 volt. Now this electrode is this half cell, or this is again coupled with another. Suppose zinc rod dipped in zinc sulfate, or copper rod dipped in copper sulfate. So to a copper rod dipped in copper sulfate, to that this hydrogen electrode is connected. A zinc rod dipped in zinc sulfate, to that a hydrogen electrode is connected. In this way, so for every metal ion, for every type of element, generally this hydrogen electrode is coupled, is connected, and from that, what is the standard cell potential is then calculated. What is the standard cell potential is then calculated. So after calculating the standard potential, you know this is taken as the reduction potential, as the oxidation potential we have taken arbitrarily 0.00 volt, and from that you can determine by coupling with it, by just subtracting with it, either from cathode cell or from oxidation half cell or from reduction half cell, we can determine what is the electrode potential, what is the cell potential of this cell, of the total arrangement, and from that we can determine what is the electrode potential, what is the standard electrode potential of that half cell. So by coupling with the standard hydrogen electrode, by coupling with the standard hydrogen electrode with other electrodes or half cells, or other electrodes or half cells, the cell potential is determined, and that cell potential when connected with single hydrogen electrode is known as standard electrode potential of the electrode. So it gives you the standard electrode potential. So by coupling with standard hydrogen electrode with other electrodes or half cells, the standard electrode potential is determined. The standard electrode potential is determined. Okay, and this standard electrode potential are then arranged in a regular way, in an increasing order or in a decreasing order. Okay, so for today up to this, in the next class we will discuss some other part.